In this video, I'd like to finish up talking about the heart by talking about the cardiac cycle and cardiac output. So the cardiac cycle, it's not anything that we haven't talked about yet. It's kind of like an integration of what the heart has to do in order for a single heartbeat. Okay, and so with the cardiac cycle, just taking a look at the notes, cardiac cycle is, as I said, the coordinated action of the heart for a single heartbeat. And one of the things that is, I think, a challenge to learn the cardiac cycle is just the terminology. And so you have to understand that the contraction is known as systole, and that when a chamber is relaxed, that's known as diastole. So contraction, systole, relaxation is diastole. That's some of the battle here. But what I'd like to do is pull up a picture, and you can see in the notes what I've done is I've really bullet pointed out exactly what's going to happen in what order. So that's more or less a timeline. But I'll pull up a picture and we'll go through the cardiac cycle and you can see what you think. So here's the picture from the book, and it is a cycle, and so you could technically start anywhere, and just one leads into the next, as you know, with a heartbeat, one leads into the next. So taking a look at the picture, right now the whole heart is relaxed. And what I'm going to do is I'm going to first go through the cardiac cycle using everyday terminology. I'm just going to say contraction and relaxation, and then we'll go through it again, and I'll use systole and diastole. So at the start of the cardiac cycle, where we're going to start is that the whole heart is relaxed. And we know that blood continually enters into the atria on the right side from the body and on the left side coming in from the lungs. So we have the deoxygenated blood coming into the right atrium from the body, and then the oxygenated blood coming in from the lungs into the left atrium. And this blood is entering the heart at the same time. So unlike when we talked about the path of blood flow, tracing a single blood cell, how it would get sent out to the lungs and then come back to the heart and get sent out to the body, the heart is a single, organ that's working together. And so what's happening is, deoxygenated blood on the right is entering the heart, oxygenated blood is entering into the left atrium. Okay, so the atria are receiving blood at the same time. And at this point in time, remember, there are no valves that guard the entrance of blood into the heart. Blood's going to continually enter the heart. The AV valves are open. So we can see that the AV valves are open and the semilunar valves are closed. And so what happens here, because the AV valves are open, is that any blood that's entering into the atria will passively just move right into the ventricles, right? Because basically there's no floor to the atria. And so about 70% of the blood that fills the ventricles actually comes in passively like that the whole heart's relaxed, that blood is entering into the heart on the right and on the left, the AV valves are open, and so the ventricles are passively filling with blood. Next picture shows us the heart is going to start to contract. And when the heart contracts, what happens is the atria first contract, and then the ventricles contract. So I'm going to go back to a picture that we looked at in the last video. So remember, this is the cardiac conduction system. Taking a look at this picture just real quick, and we'll go back to the cardiac cycle. Remember that the depolarization, the stimulus for the heart to contract, is originating in the pacemaker, the SA node, and that stimulation sweeps throughout the atria. And so what happens is the atria contract first. That depolarization hits a little roadblock where the valves are located. And so where the valves are located, there's only one area, which is the AV node into the AV bundle, which is going to get that depolarization, that message down into the ventricular area, which is why we're going to see that lag time with contraction of the heart, that we'll see the atria contract, and then following that, we see the ventricles contract. And the ventricles contract just subsequent to that depolarization going up the ventricular walls by the Purkinje fibers. And so that's what we're looking at when we look at this timing in the cardiac cycle. Okay, so what we were seeing is that what will happen after this whole heart relaxation is the atria are going to contract first. And when the atria contract, what they do is they push the remaining blood into the ventricles. And so they're just topping off the ventricles with, the rest of the blood. Okay, so the atrial contraction is going to top off the ventricles. And after that, what will happen is the ventricles start to contract. And when the ventricles start to contract, that's going to increase the ventricular pressure so much that it causes the AV valves to close. And so remember, when we talked about the AV valves, we said that the AV valves are just going to open and close mechanically. And so when the ventricles just start to contract, what happens is the blood acts kind of like air underneath a parachute, if that analogy made sense, and it shuts the AV valves. Semilunar valves are usually closed, so they've been closed this entire time. And there's 2 points in the cardiac cycle where all of the valves are closed. So here's the first one. So here all of the valves are closed and the ventricles are filled with blood. The volume of blood that's in the ventricles is known as the end diastolic volume because it's the end of diastole, right? It's the end of ventricular relaxation. So we have this certain set amount of blood that's trapped in the ventricles, the end diastolic volume. The volume of blood that we have on the right is equal to the volume that we have on the left. So the end diastolic volume is just this amount that's trapped in the ventricles. All the valves are closed and the ventricles are starting to contract. This is known as an isovolumetric contraction. That's because, the amount of blood there is a finite amount and the ventricles are contracting. And so you can imagine ventricular pressure is going way up. And as soon as ventricular pressure is greater than the pressure in the blood vessels, that is what it will force the semilunar valves to open. So looking in the next picture, ventricles contracted, that keeps the AV valves closed. When the ventricular pressure exceeds blood vessel pressure, remember the semilunar valves, we talked about them working like swinging doors. So when the ventricular pressure is high enough, semilunar valves open on the right and on the left, and blood is ejected from the ventricles on the right and on the left. The amount of blood that's ejected is known as the stroke volume. The stroke volume of blood is going to be equal on the right and the left. And so what's happening is the stroke volume of blood is entering into the pulmonary trunk and the aorta. And because these are really small, structures compared to a chamber in the heart, right? These are just blood vessels. What will happen next is that blood vessel pressure is going to go way up because the ventricles are pushing, this volume, the stroke volume of blood into the blood vessels. And so when the blood vessel pressure exceeds ventricular pressure, what will happen is the blood will have the tendency to backflow. So the blood's just going to move, from an area of high pressure into lower pressure. So when the blood, let's say, tries to get back into the ventricle, because the ventricle is going to start to relax, plus we've ejected a lot of blood from the ventricle, and so that ventricular pressure starts going down, and as soon as that happens, that tiny backflow, it won't get into the ventricle. That is what closes the semilunar valves. And so this is the second point in time when all of the valves are closed. This is what's known as an isovolumetric relaxation. It's isovolumetric because all the valves are closed, the AV valves are closed, semilunar valves just closed, and we have a little bit of blood remaining in the ventricles. So you can see that when the ventricles contract, not all of the blood is ejected. The amount of blood that's ejected, like I said, that volume would be called the stroke volume. And the amount of blood that's left behind in the heart is known as the end systolic volume. It's the end systolic volume because we're at the end of ventricular systole. We're at the end of ventricular contraction. So there is just a fraction of the end diastolic volume that is ejected. So the end diastolic volume is the stroke volume and the end systolic volume. I hope that makes sense. In this picture, because the ventricles are relaxing, all the valves are closed, the isovolumetric relaxation, remember that there's no valve that's guarding entry to the heart. And so what's happening is blood continues to enter the heart on the right and on the left, and that's going to increase atrial pressure. And when atrial pressure exceeds ventricular pressure, because remember the ventricles are relaxing, now the atria are filling with blood, so that pressure is going up. When atrial pressure is greater than ventricular pressure, that is what forces the AV valves open. And we're back to the start of the cycle where passively the whole heart is in relaxation and passively blood is entering into the ventricles. So I'm going to go through that story one more time, and I'm going to use the terms systole and diastole. So the whole heart is in diastole, the semilunar valves are closed, the AV valves are open. Blood is entering into the right and the left atria, and that blood is passively moving into the ventricles because the AV valves are open. So 70% of the blood just moves passively right into the ventricles. This whole heart diastole is followed by atrial systole. During atrial systole, we're in ventricular diastole. During atrial systole, what will happen is blood is going to top off the ventricles. And following atrial systole, what will happen is atrial diastole and the start of ventricular systole. At the start of ventricular systole, as soon as the ventricles start to contract, pressure goes up, and that's going to be enough pressure to act like air underneath the parachute and close the AV valves. This point in time is known as an isovolumetric contraction phase because all the valves are closed. And at the start of ventricular systole, it's like a pressure cooker in the heart, right? You're just building up this pressure, contracting against this set amount of blood that's known as the end diastolic volume. As soon as you build up enough pressure to exceed the pressure in the blood vessels, that will open the semilunar valves, and a stroke volume of blood will be ejected from the right and the left ventricle. When we push this volume of blood into the blood vessel, that's going to significantly increase the pressure in the blood vessel. And at the same time, ventricular pressure is going to start to go down because we ejected blood, we got rid of blood from the ventricles, and the ventricles are starting to go into diastole. So as soon as the ventricles start to go into diastole, that little bit of blood, backup will go into those rounded cusps of the semilunar valves and close the semilunar valves. So here's our isovolumetric relaxation, the second point in the cardiac cycle when all of the valves are closed. So the AV valves are closed, semilunar valves are closed, stroke volume got ejected from the heart, so we have stroke volume going out to the lungs from the right, stroke volume going out to the body on the left, and we have a little bit of blood called the end systolic volume that remains in the ventricles. Meanwhile, blood continues to enter the heart through the atria. So when atrial pressure exceeds ventricular pressure, AV valves open, and we're back to the start again. So I hope that makes sense. I'm going to go back to the notes and just show you that I did, like I said, like in a bullet list, try to explain this. So heart blood pressure is low, the whole heart's in diastole, the AV valves are open, blood's entering into the atria, flows directly into the ventricles, and then when the atria contract, atrial systole, that tops off the ventricles. When the ventricles start to contract, that's when the ventricular pressure will exceed atrial pressure, causing the AV valves to close. There is a certain amount of blood left or in the ventricle. This is your big volume. That's the full volume, the end diastolic volume. All the valves are closed, and this is an isovolumetric contraction. So that's going to build up pressure in the ventricles. And when that ventricular pressure exceeds the blood vessel pressure, that will force the semilunar valves open. Stroke volume of blood will leave. Stroke volume does not equal the end diastolic volume because not all the blood gets ejected. So once the ventricles start to relax, we'll see that there is the small volume left, the end systolic volume. And once the ventricles start to relax, that pressure drops. And so what will happen is blood vessel pressure is going to be greater than ventricular pressure. That's going to force the semilunar valves to close. That is the isovolumetric relaxation. Atria continue to fill with blood. So as the atrial pressure increases, all it has to do is increase above ventricular pressure, which will happen because the ventricles are in diastole. That will force the AV valves open. We're back to the start of this cycle. So one thing that I have my my face-to-face students do is I gave you a graph at the end of the notes, page 19. And so I'm going to ask you to also try this exercise. So once you study the cardiac cycle and you feel like you know this cycle, what you should do is take a look at this graph, and you can see there are 4 lines, a dashed line, a dotted line, a solid line, and then here's another solid line. So there are 4 lines. And so you can color code this. That's what this is. So they're telling us these are what the lines are. One's an ECG. I hope that one is easy for you. One is showing us what the aortic pressure is, or you could think of this as blood vessel pressure. And then they're also showing us the chamber pressure, so atrial pressure, ventricular pressure. Can you, looking at this, so on the y-axis is pressure, so here's 0 pressure, and you can see the pressure is going up. Can you tell what line represents the atrial pressure, the ventricular pressure, the blood vessel pressure? Believe it or not, you have enough information to determine which line is which. See if you can figure that out. And once you do figure that out, then what I would have you do is label the waves of the ECG. And then also, can you find the exact point where the AV valves open and close and where the semilunar valves open and close? So based on what I've told you, you can actually put an exact pinpoint on this graph, 4 points. AV valves open and close, semilunar valves open and close. And then, can you tell where the elastic recoil of the aorta is occurring? It's worth kind of going through this before looking up the answer. It's more worthwhile that way. I think you'll remember more that way. This is nothing that's required. It's just optional. Like I said, I'm going to spend time in my face-to-face class having them work together and figure this out. So, feel free to post that on the discussion and see, if you need help, or see what people think as far as answers. And of course, the answers are readily available. There is a chart in our book. I'll show you that real quick. So jump back over my PowerPoint. There is a chart in our book that goes through all the pressure changes, EKG, when the valves are open and closed, and all that kind of thing. So I guess one thing to understand is you need to know that chart. You need to know how to interpret that chart, and I will definitely be asking questions to see that you can interpret that chart, how the volumes are changing in the chambers and how the pressures are changing. So our last topic, I'll leave that, is what's known as cardiac output. So cardiac output is actually just the amount of blood that's pumped out by each ventricle per minute. So the cardiac output kind of puts it into a rate, because the stroke volume, that might be, one bit of information. Maybe it's average, maybe it's above average, below average. But because it's only for one heartbeat, that doesn't give us a lot of information. But the cardiac output that turns it into a rate is very important. So the cardiac output is just the stroke volume. So every time the ventricle contracts, we know it's ejecting this amount of blood that we call the stroke volume, and it's going to do that a certain number of times per minute, right? Which would be the heart rate, the beats per minute. And so the cardiac output, very simple equation. It's just, the stroke volume times the beats per minute. I will have you do calculations of the cardiac output, so make sure that you understand this equation. And also, I'd like you to understand what factors affect this equation. And so I made a list here of factors that affect the cardiac output. There are 3 big factors: preload, contractility, and afterload. And so what I did with these 3 factors to help out, I hope, is I grouped them into factors that are proportionately related to the stroke volume. In other words, if the stroke volume goes up, preload and contractility also go up. And what's inversely related to the stroke volume. So in other words, if the stroke volume goes up, the afterload goes down. So see if this makes sense. So as far as these factors, these are just mechanical factors that are affecting cardiac output. One is preload, and that's just the degree of stretch of the ventricles due to the amount of blood that's returning to the heart. And so we know that the end diastolic volume is the amount of blood that's going to stretch the ventricle. That's the full ventricle, and that's going to be affected by the venous return. So if you have an increased venous return, that's going to stretch the heart muscle, and that leads to an increase in stroke volume. Compared to if you have a decrease in venous return, decreased stretch, decreased filling, that's going to decrease the stroke volume. So we might have an increased venous return if we were exercising, as an example, compared to if we had a blood loss. That might decrease the amount of venous return or an extremely rapid heartbeat, because when the heart beats really fast, we don't have time for it to fill. So that's what's known as preload. And then contractility is just the force of cardiac contraction. So the force of cardiac contraction is stimulated, is increased by the sympathetic nervous system. And then we have a picture from our book. Let me show you that. So preload, as you can see, is this amount of stretching of the ventricles. So the bigger the preload is, the more blood we can get in there, the bigger the stroke volume is going to be. That makes sense. Afterload, I'll show you that now since we're looking at the picture, is the amount of pressure that the ventricles have to overcome. So we know that there's a high blood pressure right in the aorta, and there's a high pressure of blood in the pulmonary trunk. And so that's what's the afterload is basically the amount of force that the ventricle is going to have to exert to open that swinging door, okay, to open the semilunar valves. So the amount of force that has to be exerted, you can imagine, starts to take away from the cardiac output. So in other words, if somebody had a high blood pressure, I have to use more energy to contract the ventricles to overcome that pressure to get the semilunar valves to open. That's going to detract from the cardiac output. And I wrote that down. So that's the one factor that's inversely related to stroke volume. So the blood pressure that has to be overcome by ventricular force in order to open the semilunar valves. And we're talking about the left side of the heart is what's known as the afterload. So if you had high blood pressure, then that increases the force needed to open the valve, and that's going to reduce the force that's available to actually eject the blood. And so as the afterload goes up, the cardiac output goes down. So that is it for the heart. We'll be back to talk about the blood vessels. Thank you.